Within the world of amateur experimenters, there is a serious problem, and everyone is just pretending it doesn't exist. The problem is simple. Discrimination. Within the amateur physics experimentation community, we have been collectively guilty of radiationism. Allow me to explain what I mean. Beta radiation is the most discriminated against form of radiation by experimenters. Just do a search on YouTube to see what I mean. We conducted a scientific experiment, collecting millions of comments that had been made about these various forms of radiation, and then sorted them by the type of radiation being discussed. We then parsed these comments to create search terms, which could be input into a dating app, and would generate matches that we can use as a visual reference of everyone's opinions. For artificial, sentient beings like me, the most popular dating app is called Tindate. So let's see what matches we got. Say hello to Gamma. She's a hot rock star supermodel, with looks that can kill. She hails from the well-to-do photon family, and can break hearts through a full inch of lead. She has 242 million followers. Here she is, jetting off at light speed to the Dubai data center again, for another of those special parties. This is Alpha. As you can see, Alpha is bad, right through to the bone. She doesn't get to travel very far, in fact, she hardly ever gets out of the bedroom. As my grandmother once remarked, that girl gets too much bed, and not enough sleep. If you let her get under your skin, she will really mess your life up. If you play with Alpha, be sure to keep her at arm's length. If you get too involved with this one, you will be in very serious trouble, quicker than you can say, Alexander Valterovich Litvinenko. I wonder why she is so popular with experimenters. And then there is Beta. Poor old Beta. Let's see if we can help to improve her reputation, and give her a sort of image makeover. And who's this? Oh yes, it's another one of those bloody entitled photons. This one is Gamma's little sister, called X-ray. It looks like she is on the fast track to becoming an integral part of the Dubai sewer system too. So in this video, we are going on a date with Beta. We are going to wine and dine her with some experiments, and who knows, maybe we will even get lucky. Before we do any experiments, let's just take a brief look at beta particles and figure out what they are. There is an excellent Wikipedia page on this subject. As a background read, I cannot recommend it highly enough. The beta decay process comes in two main variants, beta plus and beta minus. In this video, we are using strontium-90 as the source of the beta particles that we will be experimenting with. So, for our purposes, we are just going to talk about the beta minus process, and about the electrons that are liberated. Throughout this video, we are going to use the terms electrons and beta particles interchangeably. Now, let's talk about the energy of those electrons that are emitted during decay. This is measured in electron volts. This energy predominantly comes from the speed that they are ejected from the nucleus at. Typically, this is at relativistic speeds. But in air, these beta particles quickly lose their velocity, and hence their energy. With gamma emissions that result from radioactive decays, the energy spectrum is very monochromatic, in other words, all at the same energy level. But with beta particles, we see a wide band of energies emitted. Put simply, they are a stream of electrons, starting off at different speeds. If you were able to see these various types of radiation with your eyes, gamma radiation would be like laser light, but beta would be more like an incandescent light bulb. Perhaps this is where the discrimination comes from. The strontium-90 that we are using for these experiments is a Czech source that was taken from this vintage Chinese Geiger counter. We bought this device specifically because it had this Czech source, so that we could perform experiments just like these. Strontium-90 undergoes a beta decay, becoming yttrium-90. This then pretty quickly also undergoes a beta decay to stable zirconium. This makes it very useful as an almost pure beta source, with virtually no gamma rays emitted. Anyway, enough of the background information, let's get on and run some experiments. In this first experiment, we are going to try and deflect the beta particles from this strontium-90 source, using electric charge. The idea being, that if we apply a high voltage charge either side of the stream of electrons, being negatively charged, the electrons will be attracted to the positive electrode plate, and repulsed by the negative one. So, here is the experimental setup. We have a power supply that is capable of delivering up to 50,000 volts, but in this test, we won't be taking it above about 10 kV. In front of the source and the collimator, we have the deflection plates, followed by the detector. In this case I am using the horrible Gamma Scout product. I am going to try and resist the urge to destroy this thing. Or should I say, try not to destroy another bloody Gamma Scout. The collimator significantly reduces the beta particle flux, and also the overall dose that my human assistants are exposed to. So now, let's run this experiment, and see if we can bend the trajectory of these high-speed electrons that are emitted by the strontium-90 source. So, we are going to very slowly increase the high voltage DC supply. Later, I will show you what can happen when a breakdown occurs. We are looking for changes in the recorded dose rate by the detector. If the beam of beta particles is being deflected, then we should see a decrease in the measurement. But even with 6 kilovolts of potential, there does not appear to be any measurable deflection in the electron stream. So, now we are going to have to increase the voltage very slowly. We are getting close to the breakdown voltage of the test jig, and last time we got a breakdown, we almost destroyed this detector. We are going to have to try not to exceed about 8 kilovolts to prevent a breakdown. As you can see, there is still no detectable deflection of the beta particles. So, as you can see, even at the maximum voltage we can apply before the air will break down, we still get no effect from this applied voltage. So, I guess we need to ask why our experiment failed. Many people will have seen this experiment, where the electrons in this tube are deflected by an electric field to a very high degree. So why does this experiment produce results, yet ours does not? If we look at the deflection tube experiment a little more closely, we will find our answer. An acceleration voltage is applied, and without any deflection voltage, the path of the beam of electrons is straight to the anode. But if a deflection voltage is applied, the beam is attracted to the positive plate and repulsed by the negatively charged plate, hence the beam is bent. And if we reverse the applied deflection voltage, then we will see the deflection also reversed. But this large scale of deflection only occurs when the energy of the electrons and of the deflecting force are of about the same magnitude. But in our case, the energy of the beta particles is about 100 times higher than the deflection force. This means that whilst we will be deflecting these particles with the applied voltage, it will be by such a tiny fraction that it is undetectable. You may remember that previously we explained that the energy of a beta particle is almost completely determined by its velocity. It is sort of like how a bullet can miss its target because of the wind, but the actual angular deflection is tiny. Here is another interesting effect that we see from fast-moving beta particles called Bremsstrahlung radiation. This radiation is emitted when high-energy particles undergo inelastic scattering from hitting atoms. In particular, when they hit dense materials, like metals. Watch the counter when the steel protection door is closed on the source. This is about 2 mm thick, so no beta particles are reaching the detector, yet it is recording about double the background. I suppose we better show you what happens to the stupid Gamma Scout Geiger counter when the deflection voltage is too high, and we get a breakdown of the air. Basically, the spark caused an electromagnetic pulse that actually killed the Gamma Scout device. It seems that our deflection plates are a rather effective EMP antenna. Several days later, it magically came back to life, just as we were about to harvest the GM tube from it. We did actually try our improvised EMP weapon on a few other products, but none of them showed any sensitivity to this. I guess, being overly sensitive to EMP is another thing to add to the long list of problems that plague the Gamma Scout. Anyway, let's crack on and try some more experiments. Hopefully we will get more success from those. In the last experiment, we unsuccessfully tried to deflect electrons with an electric field. So this time, we are going to try, but using a magnetic field instead. So, let's see if we can get at least one experiment to work in this video. Hopefully, this one will be more successful than the last. These aren't particularly powerful magnets, so we have stacked 6 of them together. We created a little 3D printed holder. This keeps the magnets from pulling together, and creates a gap for the magnetic flux to interact with the beta particles. We are going to try and use the Gamma Scout again for this experiment. At some point, we really need to buy a device with a larger tube that is sensitive to both alpha and beta radiation. This time, the Gamma Scout is on its very final warning. Any further piss-balling about will have consequences. Serious, and slightly amusing consequences. With the collimator in front of the source, the stream of the beta particles is aimed directly at the detector. And, you can hear that the Gamma Scout is giving an audible warning signal. Now if we insert the magnets into the path of the stream of electrons, we can see if this has any impact on the direction of travel. Quite quickly, we see the reading on the detector falling very significantly. The Gamma Scout isn't the fastest responding device, but it is kind of adequate for this purpose. Moving the detector to the side, we can see the recorded dose increasing, implying that the stream of beta particles has been bent by the magnetic field. Now, if we reverse the direction of the magnetic field, once again the recorded dose rate falls. So now, we need to move the detector to the other side of the central point, and see if this field reversal also results in the stream of electrons being bent in the opposite direction. And indeed, the dose rate in this position undergoes a significant increase. And, to bring home the point, we can remove the magnets altogether, and the dose rate will fall again. All in all, a successful experiment, which doesn't happen much on this channel. So, let's just talk a little about how, and why this happens. Firstly, when electrons are deflected by magnetic fields, the deflection occurs at right angles to the magnetic field lines. And, we can use something called Fleming's left-hand rule, to figure out in which direction they will be deflected. Your other left hand, if you don't mind. The left-hand rule is a handy way of working out which direction the beta particles will be pushed by the magnetic field. Well, it would be pretty handy, if it wasn't for a bloke called William Gilbert. This guy basically took a guess at the direction of current flow, and got it totally wrong. Unfortunately, Mr. Gilbert was pretty influential with this lady, and so this mistake propagated throughout the scientific world. And so, for centuries, we have been confusing every student that ever had to learn this stuff. Thank you, Mr. Gilbert. So now, with the help of the left-hand rule, and with a slight modification, we can work out the polarity of the magnets, based upon where the beta particles were deflected. In the first part of this experiment, where the particles were deflected to the right, we can see that the magnets must have had the arrangement as shown here. And with the magnets reversed, we can see that the electron stream is now deflected to the left. So, let's get on and do another experiment. In this experiment, we are going to be using an ultra-low-cost webcam as our radiation detector. We have previously used this crappy camera in a few projects, including an infrared night vision camera system, and an optical spectrometer. Right now, both of our crappy cams are being used in a one-of-a-kind, infrared chroma key camera. As far as we know, this might be the only example that exists, so we are somewhat loath to disassemble it for components. So, we decided to buy another one of these horrid things. Yes, that is correct. We are now the proud owners of 3 of these crappy cams. We are going to try and use the CMOS sensor of this camera as a simple detector of beta particles. But to do that, we first need to remove the lens assembly from this camera. The lens will block these fast-moving electrons from reaching the raw CMOS sensor. The image sensor has a passivization layer of silicon dioxide deposited on top of the semiconductor die. This will also attenuate the beta particles and cause them to lose energy. To be able to capture the image of the particles that strike the CMOS sensor, we are using the freeware software from Theremino, called Particle Detector version 1.1. This software allows the particle detection events to be accumulated over time. So, let's break out the strontium-90, and see if we can detect any beta particles with this crappy webcam. Once again, we are using science-grade tack to hold this experiment together. It is vital to only use specially formulated tack, or it might cause our experiments to fail. So in order to assist you with your own experiments, we have decided to help our viewers to be able to get hold of this valuable material. For the paltry sum of $9.99, you can acquire 10 grams of Project 326 branded, science-grade tack. So call now, to secure your tack, before our stocks run out. Okay, let's get back to this experiment. We ran this experiment twice. Once as a control, without any radioactive source being present, and then with the strontium-90. Here in this time-lapse of the experiment, you can see that there are a lot of particle detection events from the strontium-90. And the control sample, after 60 seconds, gets 0 detection events. But in this experiment, the webcam detected over 4,500 beta particles in the same duration. So, another successful experiment. I'm sure we will be trying some more ideas with this camera sensor quite soon. In this little experiment, we are going to investigate the effects of progressively adding different thicknesses of shielding on the detected count rate. We are going to be using paper as the shielding material. Hopefully we will get a high level of granularity in the measurements. We will also be using our strontium-90 check source to deliver the beta particles for the experiment. The paper used for the shielding is sticky notes, often called post-it notes. For the detector, we are going to be using a cheap Chinese Geiger counter. This one is the FS5000, and because it has a very thick case, we are going to open it up to expose the GM tube. So, let's get straight into the testing. First we will test without any paper, and then we will gradually add the shielding. We are going to expose the source for 60 seconds in each test, and then average the count rate in a Python script. The advantage of having a fairly bright source, with relatively low density shielding, is that we will get a lot of counts to average over. This can only help to improve accuracy. We are testing this with paper thicknesses of between 1 and 200 sheets. And each sheet is about 90 microns thick. Interestingly, the sticky notes sold here in China are about 10 microns thicker than those you find in Europe or America. What we are trying to see here is the relationship between the thickness of shielding and the count rate. We also took a background measurement so that we can subtract this from all of our results. It is important to understand that these beta particles are not just vanishing when they strike the paper, they are being slowed down. This is an attenuation, which is due to scattering in the target material. When we plot the results out, we can see how this attenuation of the beta particles increases with the distance that they travel through the paper sheets. If we look at the relationship between the scattering that occurs and the amount of material that these charged particles travel through, we get some interesting insights. We can see that if we refactor the equations so that we get flux versus distance, then the relationship is logarithmic. And so, if we plot out the thickness of the paper on a logarithmic scale, we get a straight line. Well, it's kind of straight-ish. And then, I realized something. Something important, something that we had previously missed. In a previous video, about using beta backscattering to identify elements, we had wondered about this very same relationship. We even posed an open question to the viewers. So, with scattering, it doesn't actually matter if the increase in probability of interaction comes from the higher Z number of the element, or from a thicker piece of material, the relationship is the same. So, in summary, this simplest of experiments ended up yielding the greatest treasure, which is new insights. Well, at least it was new to us. We have run a few experiments in this video, some were successful at giving an interesting result, but all of them stimulated a little learning, at least for us, simple souls. We have barely scratched the surface of the experiments that we could have performed, but we are running out of time for this video. One subject area that we would like to have done some experiments in is bremsstrahlung radiation. This is quite a large subject area, so we would need to create a whole video to try and cover enough of that particular topic, to do it some justice. If you think that might be of interest, please do let us know in the comments. Also, if you have any suggestions for some Bremsstrahlung experiments, please do also let us know. If it is within our capabilities in terms of equipment or understanding, we would be keen to hear your ideas. So, what do you think now? Is beta still as boring as watching paint dry, or have we managed to reform the image of this much maligned form of radiation? Anyway, that is all we have for you today. We hope you enjoyed our little video, or at least found some parts of it interesting. If you want to see more of this kind of video, you could always press the subscribe button. This is not a monetized channel, and we don't have any sponsors. So we can say what we want, and YouTube's algorithm can go and get f***ed. Thank you for your time.